Round part, square stock. Let's make it on a mill. Hello everybody and welcome back to AtMan Unlimited. Before we start this episode, I first want to give a shout out and say thank you very much to the viewers that are supporting our channel. We got a few emails from a couple of viewers asking how they can support the channel monetarily, so we appreciate that and thank you. And then we also had a few people sign up for our Patreon page, so thank you again. It really helps out and it is greatly appreciated. So we're going to make a part, and I'm going to split this into two episodes. This episode I thought we would go into the office and I'll talk about how I modeled this really quick. I'm not going to go really in deep into the modeling and really in deep into the cam, but I wanted to talk about how I look at a part and then decide how I'm going to make it. So with that said, let's go down to the office and we'll check out some modeling and some cam in Fusion 360. So we're back in the office here. Let's jump into Fusion 360 and see how we modeled this part. So here I've got Fusion 360 open, and I already modeled this part. I'm just going to walk through the timeline to show how exactly I modeled it. Now anytime I see a part that has a round feature to it, I instantly think revolve. So revolve is the easiest way to sketch a round part that has some type of profile to it. So I first started with a sketch, and I measured out the part and then sketched it to generate its profile. Then after we've got the profile, I did a revolve. So very quickly and easily with one sketch, we were able to generate the general profile for the part. Once we have that, it's pretty easy to just go through and start adding the extra features that this part has. So the next step, I made the revolve into a component, and then we added the thread. The thread option on Fusion 360 is actually pretty cool, how you can just do a depiction of the thread on the part. The one thing that I wish that they would do though, and you'll see why later on, is when you tell Fusion 360 to generate the thread but not actually model it, only project it, they don't give you a lower edge here. And that would be pretty handy to have, that lower edge. So then after we have the thread, we're going to do an extrude. Now what I did is when I sketched the part, I also sketched those cross holes in it that are here and here, and then I just extruded the holes through. Now those aren't too critical. We're actually not going to cam those holes. They're not precise holes, they're not critical holes, they're just for airflow. So I'm just going to put those holes in with a drill press after the fact. So they're not going to be a big deal. So then I generated another sketch, and this sketch is just on the top to make the hole that goes through the part. And then we made a hole there, so there's the hole that goes all the way through the part. Then I generated a third sketch, and that's going to be for the hex bolt on the bottom. Now before you extrude this, I did a chamfer. And the reason why I did this before I extruded it is I have this nice edge right now that I can select and then chamfer. So we add the chamfer first, and then that just gives us a nice looking bolt head when then we do the extrude for the bolt flats. Now anytime that I'm modeling and I have vertical corners here, because we're going to make this part on a CNC mill, anytime you've got those vertical corners, it's easy to just add a radius to it, and now when you profile that part, it will follow the radiuses and deburr the part for you. So anytime you got a vertical surface, it's always good to throw a radius on there so that you get a deburred part right out of the machine. And no matter what machine you have, it doesn't cost you anything. It's just a slightly different tool path that it's going to take. And then the last operation is just to put an inside chamfer on this hole here. Now you noticed I didn't chamfer any other edges on the part, and I'll show you why in the cam. This is another weirdity with Fusion that I wish we could get fixed as well. And if you have a sharp edge, the chamfer tool paths are pretty good. They work well. But as soon as you model the chamfer, you start getting some weirdness in how you select the chamfer to be machined. And I'll show you that when we go to cam the part. So there's all the modeling for the part. And again, it's a round part, you know, except for the hex head on the bottom and the cross holes. This is screaming lathe, but you know what? We got a mill. We want to make the part. We'll make the part. It's not that big of a deal. We'll be able to make it pretty good. We can get concentric circles that are interpolated within about 5/10, so it's good enough for this part. So that's the modeling. Let's go over to the cam side and talk about how we set this up and how we're going to run this part in cam and then in the machine. So let's do that next. So we switched over to the camming environment, and let's talk about the setup first for this part. So anytime that I'm going to make a part, the first thing I do is I look at the finished part and I think to myself, looking at this finished part, what's the easiest way to hold this part when it's finished? And that answer drives a lot of stuff. So in the case of this part, my feeling is that holding on to this bolt head is going to be my best option. I can use a standard set of vice jaws in my vise. I've got a nice 90-degree engagement here where I got a flat and a flat, so that, you know, the part isn't going to want to lever out of the vice jaws when we push on the top of the side of it. Giving you a little ride. So I think what I'm going to do is, you know, almost every part you make is going to be two operations. So I'm going to do this part of the part as operation 1. I call it op 10. And then this side of the part will be operation 20 or op 20. So in my setups, I've got op 10, and then I've got op 20, and I have my stock configured. Now, I just went out to the back and grabbed just some general stock to make this part out of. So I've got kind of an oversized piece. I'm not going to bother to throw it in the bandsaw. We're just going to go at it with the 2-inch face mill, and we'll just buzz the top of that thing off really quick. So for my first operation, I'm just going to hold the raw stock in the vise starting about here, and then this whole thing is going to be in the vise. So I got a really good hold on this. It's not going anywhere. So I can just go, you know, whole hog at it. So we're going to use the 2-inch face mill, and then there's the tool path for it already. And we're going to go at this at like 100 inches a minute with an 1/8 of an inch step down. You know, it's like a 7 or 8 thou chip load. So we're going to throw some power into this thing and just rip the material off. That's all we're going after. And then, my mouse keeps sticking. And then at the end, we'll slow everything down and just do a finish pass so we get a nice finish. After that, we're going to stick with the same 2-inch face mill and then rough the stock out. Now, a lot of people will want to switch to tools that are more right size for the task. In my mind, right size tools is the biggest tool that I can fit in there to get the highest rigidity and just rip the material out of there. Again, we're going to take 100 inches a minute, we're going to step down an 1/8 of an inch, and we're just going to get rid of this material. We've got a good hold on the part, we got tons of rigidity in the tool, it's an insert based tool, so we get good tool life, you know, lower costs. We're just going to rip the material off. Why change tools? So we're going to do that with the bolt, we're going to do that with the flange, and then now we're going to switch over to a finishing mill. So we're going to switch over to a 3/4 inch you know, square-ended standard end mill. We'll walk around the bowl head, we'll walk around the flange, then we'll add the chamfer to the bolt head. Now, here is where the chamfer thing comes into issue. You've got two options when you're doing chamfering in Fusion 360. And option one is the 2D chamfer toolpath. Option two, before 2D chamfer appeared, was that you do a 2D contour, and then when you select the chamfer tool for 2D contour, it allows you to specify the chamfer width, just like the 2D chamfer toolpath. Now the difference between the two of them is that if you do a contour and there's an obstruction in the way from like a corner or another sidewall of the part, or the part goes up a little bit where the chamfer mill will run into it and smack it, the 2D contour won't detect that and it'll just break the chamfer mill off for you. So you got to watch out for that. The 2D chamfer toolpath won't do that. It will detect that, oh hey, there's a wall there, or there's another feature on the part there that's preventing the chamfer mill from safely making that geometry, and it will stop and walk the chamfer mill out for that instance of the profile. So those are the differences. There's pros and cons to each one of them, and I use them kind of interchangeably depending on what I'm doing. If you have the chamfer modeled already, I find it better to use the contour toolpath rather than the chamfer toolpath. And then to get it to work, for some strange reason, I use this stock to leave, and I set the stock to leave to the same as my chamfer width, and I select the top of the chamfer. And what the stock to leave will do is it will force the toolpath to go to the outside of the chamfer, and then the chamfer will be correct and your toolpath will end up correct. So it's kind of weird how it works when you have the chamfer modeled. Other camming packages that I've used, you just click on the face of the chamfer and it does it. I don't know why Fusion doesn't do that, but you know, it would be nice if we could just click on the chamfer face and bam, you got a chamfer. So that's the kind of weirdness for the chamfer. The other difference is, if you notice here, I've got, I'm going to go around the horn twice here. And the reason for that is that's a 50 thou chamfer. I'm using a 1/4 inch chamfer mill. It's a little bit too much material to bite off in one shoe without chipping up your carbide. So I'm going to take 2 whacks at this and to finish it up. The 2D chamfer toolpath won't allow you to take multiple passes. It's just not in there. Okay, so again, that's the difference between contour chamfering and 2D chamfer toolpaths. You know, use which one's going to work for your specific instance. So then after we chamfer the bolt head, we're just going to throw a chamfer on this edge here. I try to do as much chamfering as I can in the machine. Let the machine do the work for you. Put the material in, press the go button, get as close to a finished part out as you can. Okay, so that's going to be our first operation. Now, for my zeros, if we highlight our operation, you'll see that my X, Y, and Z zero are on this back corner. So when I go to put this in the vise, what I'm going to do is I'm going to set the 0 in the machine as the bed of the vise, and then I'm going to set my XY0 to the back corner of the jaw, and then I'll put a little hunk of metal over here to space it so I don't cant my jaw when I tighten down on this. Then I just throw the material in, tighten up the jaws, press go. Got a good 0, we're good to go. So now once we have that operation done, it leads us on to Op 20. Now Op 20 is going to be a little bit more difficult. What I did here is this plane is going to be Z0, and that's going to be the top of the vise jaw. And then I made the XY0 the center of the part. Okay? And the reason why I did that specifically is so that when I flip the part over, what I'm going to do is I'm going to have a pretty good surface here because I actually drove this tool path for this contour down past this flange as low as I could go without hitting the vice jaws. My vice jaws, it's just a Curt D688, so they're roughly 1.75 inches tall. So that's what I use for a number so that I make sure I don't run into my vice jaws. I don't make the extra effort to model the work holding unless I'm doing fixturing or some complex work holding. If I'm just putting the part in the vise, you know, if you're having trouble figuring out what your vice jaw clearances are, maybe we should study a little more. Okay, so what I'm going to do is I'll just take a dial indicator, or I'm sorry, a test indicator, and just sweep this bottom part and then zero that zero in that way. So that's how I'll find that zero. Now the top of this part is actually pretty challenging. And it's not challenging because it's complex geometry or it's hard to make. It's challenging because you need to think about rigidity and chatter. If you recall our 100th subscriber plaque, we underestimated our rigidity a little much, and we got some chatter with the big face mill we were trying to do. So anytime you make a part, you have to always keep this in the back of your mind. When this is in its raw form of stock, this is about 1¼ inches by 1¼ inches, and it's sticking up about 1.5 inches. That's going to be pretty rigid. It's not going to be bad. As soon as I rip all this stock off and get down to this tube here, which is about 1/4 inch in diameter, the rigidity of the part is gone. It's gone. So we want to think about that during our machining operations. And if you're doing lathe work, same thing applies. As you turn this shaft down, this is going to start getting flimsy. Okay? So we want to keep that in mind while we're doing our tool paths. So what we're going to do is first, we're just going to face it. Okay? So we left a little bit of stock from op 10 on the bottom, just to get rid of our saw marks, square it up real nice, and face it. Then after I face it, I'm going to spot it and drill it. Now why would I want to drill the center out first? Well, a tube is much more rigid than a solid bar. And if you don't believe me, you can do some experiments. You can take a solid rod and a hollow rod and support it at each end, and then put the same amount of weight on each of them, and you'll see that the solid rod will sag much sooner than the hollow tube. The hollow tube typically won't deflect, it will just catastrophically fail. So by drilling this hole first, we're going to help our rigidity problem. So that's why this is, one of the first operations, to drill the hole. Then what we're going to do is we're going to switch back to our 2-inch face mill again. It fits, why not use it? And we're going to employ a little bit different of a tool path. So again, this is also why I'm using the 2-inch face mill. What I'm doing here is, rather than using a standard end mill and trying to mill as far down here as possible to use as much cutter as I can, again, tool life, we're thinking about tool life here, I'm going to use a face mill instead, which is designed to only cut, thin slices off at a time, and I'm going to spiral this thing down and just peel off all this material around this tube. So what I'm doing is my cutting forces are going to be concentrated down here where the part's more rigid and I've got all this stock left. And notice I'm not doing the whole thing yet. I'm only going a little bit farther than that thread. Okay? Now once I do that, then I'm going to switch over to a regular mill, because that face mill has a pretty large radius in it, and the face mill is not going to give a good finish here. So I want to switch to a regular mill and then just finish this one little part here. I want to chamfer it, and I want to thread it. And the reason why I want to do all that now is, again, it's all about rigidity. I've got all that stock down here that's making this part rigid right now. I just have this little tiny 1/2 inch piece sticking up. It should be rigid enough to be able to complete all these machining operations without chattering. Then, and only then, when I have all these operations finished, am I going to rip off the rest of the stock. And this is the only operation that I'm going to do. I'm going to use the 2-inch facer, And we're just going to spiral down this thing and then all the way down to the bottom. Now you ask, okay, well, you know, is that going to take a lot longer to machine it? It's going to take a little bit more time, but not as much as you think. So again, I'm not going to be running this at 100 inches a minute, taking an 1/8 inches at a step, okay? I'm only going to be running this at 50 inches a minute, and I'm only going to take 30 thou at a step, so much, much lower cutting forces here. Again, I'm really concerned about rigidity for this part. But even that, this operation is only 6 minutes. So in the grand scheme of things, again, we're making 2 of these. We're not making 100 or 1,000. We're making 2. So keep that in mind as well when you're trying to figure this out. If I were making 1,000 of these, I would not be milling them. I would send them out, you know, and have somebody else with a lathe make them. It just doesn't make sense to make a lot of these on a mill. 2, yeah, I got a mill, we'll make it. Okay? So then once our shaft is milled, then we'll do that flange here. Okay, we're not going to do this area here. We're not going to do this area because, again, this face mill has a very large radius on the cutting edges. Then we're going to switch to a standard end mill. So again, this is just our 3/4 square-ended end mill. And then we'll do this face here. Okay, I'm not going to worry about this face here. It's okay if there's a radius there. The moisture separator sits on this face and then it centers itself on this edge here. So that's the critical dimension of the part. If there's a fillet in here, it actually is going to make the part stronger. So we're not going to worry about cleaning that up at all. And again, once I take all that material off, I don't want to touch this thing, because as soon as you touch an end mill to this whole length, it's just going to take off and start singing on you. Yeah, the surface finish from the face mill isn't going to be the best, but it doesn't matter. It's inside of a moisture separator with a sintered bronze element over it. You're never going to see it. It's going to have no bearing on the function of the part at all whatsoever. So, you know, that's how we're going to make this part easily. Then the last operation we're going to do, this little slope here, I think is pretty important. It helps channel the airflow inside the moisture separator. So we're not going to do anything fancy with a bullnose mill or a ball mill. We're just going to do the square-ended mill, and we're just going to take thousandths of an inch chips at it and just you know, chip it off. Again, we're making 2 of these. The machining time is 9 minutes. You know, it'll take me longer to, you know, get a ball mill, or I would have to use a bullnose mill to be able to get this geometry correct. And it would have to be a fairly small radius bullnose mill. Again, adding an extra tool in the machine, setting up an extra tool for, you know, saving 9 minutes per part, so you're saving 20 minutes. You know, I'm making 2. So that's my general thoughts on how I go about, you know, figuring out tooling operations, you know, setup operations. We put quite a bit of thought into how to make a part ahead of time so that when we make it out to the machine, we can make that part successfully the first time. Your production volumes of parts will dictate how you code and cam your parts. In this case, I only need to make 2 of these, so I'm not looking to make this part the fastest, most efficient way. What I'm looking to do is I'm looking to make it reliably so that I can get it in the machine, get it made, and get it out of the machine the first time. Yes, I'm a little conservative, and that's okay, because if I try to push a part where I'm only going to make 1 or 2, and I make a mistake and I push a little too hard, now I've just doubled the time it took me to make that part, because I have to reset it up again, get some different material, etc., etc. So your end goal will drive how you cam a part. So I hope that you found this video helpful, and you can kind of see my mindset of when I cam a part. Your solution may be completely different. That's one of the really cool things about machining, is that every machinist comes up with a slightly different way to make the part, but at the end of the day, the part gets made, it's to print, you know, customer will be happy. This part is my part, so I'm the customer. So stay tuned on the next video. We'll throw the stock into the machine, we'll push the go button and watch some chips fly. Thanks for watching, and again, thank you for supporting the channel.